All right, we'll take a look here at example 4 now, which is where we want to consider this parameterization. R of uv equals 2 cosine u to sine u, comma v, which is parameterizing the surface of the cylinder, a cylinder of radius 2 centered at the origin. So let's go ahead and talk about the grid curves here. So what is a grid curve? Well, a grid curve is the path that is drawn on the surface of, on the surface that's being parameterized. So for this particular parameterization, what we want to do here is take a look at a particular path. So let's take a look at the u equals a constant grid curve. So in other words, if we fix one of the parameters, so let's say we fix u. So u is some value. Let's call that value u naught. Then our parameterization looks like this. Since u naught is a fixed but arbitrary value, we really go from a function of 2 parameters down to a function of 1 parameter, because this u naught is now fixed, so only v is free to vary. So we go from a 2-dimensional parameterization down to a 1-dimensional parameterization, which means that this will be parameterizing a path, something that's 1-dimensional, not a surface. So this would look like 2 cosine of this fixed value u naught, so we can think of it as a fixed angle, so to speak. And then we'd have 2 sine of u naught v. So v is varying, but u naught is fixed. Okay? So what does this trace? Well, this is some fixed number. This is some fixed number. So if we look at the first 2 components of this path parameterization, this is specifying a location on a circle of radius 2 centered at the origin. So if we think about this, if this is the xy plane, then we can think of a circle of radius 2, okay, like that. And then this, let's say we have some angle, oops, let's do this in red. Maybe this right here is some angle u naught. Then it's really this point on the circle that these 2 components are specifying. But that's a fixed point because u naught's not varying. U naught is fixed. So this is some fixed location on the circle. And then what does this component do? Well, the z component's the only thing that has a parameter in it that's varying. That is a non-constant. So what will happen is this will go over its range. So no range was specified here. No range is specified. So we're free to make some assumptions here if we'd like to. We could be so loose as to say that v would vary over all possible values. Okay, well, what would happen then? If v is allowed to range over, let's say, all real numbers, negative infinity to infinity, what will happen is this will draw, well, first of all, this would come out of the screen and into the screen forever. It would draw a straight line. So if we think about this actually taking place in 3 dimensions, however, what is our picture? Well, in 3 dimensions, we have something like, maybe I'll draw this off to the side right here. So here's our circle. Right, there's our circle of radius 2 centered at the origin. And here's our fixed value at an angle of u naught. What's going to happen is it's going to draw a straight line up and down forever. unless we specify some particular range here. So for us, let's actually go ahead and specify some range here. So over here, I'm going to add, let's go ahead and just say, actually, let's add it right here. So let me just say for u comma v in 0 to 2 pi Cartesian product with, let's say, 0 to, I don't know, h. Some fixed positive real number. In which case, this would change slightly and we'd get something that looks like this. And this stops at some z value of h. So it looks like this type of grid curve is just a straight line up and down in the z direction. So first you go to some fixed angle on the circle, so maybe it's over here, and then we'll draw a line of length h in the z direction. And this happens at every single u naught value. So at every single angle here, we get these little lines drawn. And you can see that this will actually draw the surface of the cylinder all the way around. So that's the one grid curve. Now the other grid curve, v equals a constant, so v naught, let's say some fixed v value. This would be r of u comma v naught. So now the angular parameter u is free to vary. Oops, that should be a u. But this is fixed. Excuse me. So the angular parameter is free to vary, but the height on the cylinder is fixed. So let's actually go ahead and complete this cylinder. Let's go ahead and just think about drawing this cylinder all the way out. Not my best cylinder, that's okay. So what this is going to be effectively is we're going to travel to some height, let's say right here, let's say this h value. So this distance here is some v naught. Then what's going to happen here is this is fixed, but we're going to draw a circle now at this height. So this would correspond to a circle being drawn like that. So the circle's drawn like that, and the straight line is drawn from bottom to top. So these two curves, the circle and the straight line up the side of the cylinder, they are the grid curves of this parameterization. They are the curves that are the result of fixing one of the parameters to a constant at a time and allowing the other parameter to range freely. Okay. So for part B here, compute the partial derivatives and their cross product. So if we go ahead and calculate our partials, our u will equal negative 2 sine u, 2 cosine u, 0. Our v will equal, what are we going to have here? 0, 0, 1. Their cross product here our u cross our v will be equal to, this should be, let's see, I'm going to do this one kind of quickly here. So this one, this will be 2 cosine u, 2 sine u, 0. Okay, So, what is the significance of these three quantities? Well, let's take a look at the first one, RU. So, in this parameterization, we're differentiating with respect to u. So this is saying this is the rate of change of r with respect to u. So remember, what happens when we take a partial derivative? When we take a partial derivative of something with respect to, let's say, u, we are pretending for the moment that only u is a variable and all other entities encountered or quantities encountered are constants. So this partial derivative is found under the assumption that only u is allowed to vary and everything else is a constant. Well, let's look over here in part A. Which one of these two things is assuming that u is a variable and everything else is a constant? That would be this. Here we have set v equal to some fixed value, a constant, and we are allowing u to be the variable here. So what curve did this produce? This produced the circle. So this right here, this RU, this is a tangent vector to this path here. So if we imagine this path going around and around in this orientation, then if we freeze time at any location, your line of sight or your tangent vector is that. On the edge here, that's our tangent vector. Back here, that's our tangent vector. It's our line of sight as we go around the circle. So this represents the tangent vector to the grid curve, where u is allowed to vary, but all others are fixed. Similarly, this is our tangent vector as we trace this line here. Because if we freeze time at any location, like let's say right here, what's our line of sight? Our line of sight is this direction, a straight line. And this is a straight line. This is a vector that points in the positive z direction. It has no tilt in the x or y direction. Okay. What about their cross product? Well, let's think about this. We know at the let's look at where these two things intersect. At this point where the two grid curves intersect, this would be the point u0, v0 on the cylinder. Well, to be clear, this point is actually some x, y, z. In particular, it's x equals 2 cosine u0, y equals 2 sine u0, and z equals v0. This point right here is the result of plugging in u0, v0 into the parameterization, and this will spit out some vector that points from the origin to this point on the surface of the cylinder. So u0, v0 doesn't actually live on the cylinder, but we think of this point here corresponding to the u0, v0 ordered pair. So there's a correspondence. So at this location, which corresponds to the parameter, to the point in the parameter domain u0, v0, at this point we have a tangent vector on the circle like that, and we have a tangent vector on the straight line, r sub v, that points upward in the z direction. If we take the cross product of these two, we are going to get, depending on the order of crossing, we're either going to get a vector that's pointing into the circle or a vector that's pointing, into the cylinder, I should say, or out of the cylinder. So if you had a water bottle in front of you, you can just take your pencil and put it perpendicular to the surface of that cylinder. If you cross them in the one order, it points outward, and if you cross them in the opposite order, it will point inward. So, in particular, what we end up getting here is we can interpret this cross product as a normal vector to the surface. So the cross product of these partials gives us a normal vector to the surface. Okay, so let's find an equation for the tangent plane at the point that corresponds to r of pi over 4, 5. So let's think about this for a second. What do we get here? If we plug in pi over 4, 5, we should get root 2, 5. We need to know what we get for our cross product. So if we plug in this point into RU cross RV, I'll just say the point P. This is going to be the vector root 2, 5. So this is our point on the cylinder. So that would be root 2, 5. Remember, technically this is not a point. It is a vector that points from the origin to this point. It's a subtle detail, but I'm just highlighting why I'm going from angle bracket notation to this parenthetical notation. We use parentheses to denote a point in this class, and we use angle brackets to denote a vector. The distinction is relevant for notation purposes and being able to distinguish things, but ultimately it's a very, very minor distinction. And this is our normal vector. So I'm just going to write normal vector. So putting these things together, we can go ahead and say we take our normal vector components. Oop, this should be a 0, I just noticed. That should be a 0. Pardon me. That should be root 2, 0. So this would be 0. And then, of course, we'll have x minus root 2, x minus root 2, and x minus 5, which simplifies because we never have to write, and this should be a y and a z. My apologies. Really messing up this time. All right, let's double check that. That looks good to me. So this is the equation of the tangent plane to the surface of the cylinder at this point, root 2, 5.